Good evening, everyone. Welcome to the another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. Today's talk is by Krishna Chaythanya, and he will be speaking on quickest fault detection over lossy networks for industrial machinery. Krishna Chaythanya recently defended his PhD thesis at the Department of ECE IISc, where his research focused on developing quickest fault detection algorithms for cyber physical systems like networked industrial machine monitoring. Prior to his doctorate, he spent several years in the industry applying signal processing techniques to wireless communication and designing wireless networks for IoT devices after earning his master's degree from IISc in 2011. Krishna Chaitanya's research interests lie at the intersection of statistical inference, data analytics, signal processing, and communication theory. Before we move on to the talk, we would like to request the online audience to subscribe to our Google group for more information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the online audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, please feel free to unmute yourself and ask directly or type them in the chat box so that we will relay your questions. Over to you, Krishna.
Yeah, thank you, Srinivas. So today I'll talk on my PhD work. So we'll talk about quickest fault detection for lossy networks. So this is our work is motivated by online condition monitoring of critical industrial machinery. So this is Industry 4.0, which has been facilitated by advances in microtechnology, sensors, wireless networks, and so on and so forth, has resulted in this juncture in industries where now online condition monitoring of industrial machinery is possible. Why is this useful? Well, because once this results in better utilization of machinery. Condition monitoring is essentially this. Condition monitoring is essentially the following. You keep monitoring the health parameter of a machine using one of the health parameters, and see if a machine is good or bad. You only do maintenance on the machine when it is actually going to fail, and do not use any other strategies like just stop it on an average or have a fixed time and so on and so forth. So condition monitoring consists of prognosis and diagnosis. Prognosis is prediction when a machine is going to fail. Diagnosis is to check if a machine has already failed. So in this work, we are concentrating on diagnosis part. So our work is positioned in this setting where there are different machines in a factory floor. These machines all have some sensors attached to them. These sensors are collecting information regarding the health of the machine using some parameter, and all of this are being transmitted to a central controller, which is sitting either somewhere in the middle of the factory or on a cloud or so on and so forth. This kind of architecture is very common these days because this information can then be mined for several other to get several other facets of the manufacturing process than just diagnosis. So it is in this situation that our work is stationed. So we look specifically at wireless networks because the IoT networks that the industries are going to have are largely expected to be wireless. This is because you already have an industry. If you want to wire this up for a lot of devices, it's going to be very expensive. Even if you have a greenfield industry would prefer a wireless one because the installation is easier there and maintenance easier. So therefore, we are going to be looking at wireless networks. So an example of such a system already exists. For example, Schaeffler Optime condition monitoring system has this kind of a USB stick that can be placed on a sensor stationed on a machine, and this will relay health parameters of that machine to the cloud. So something like this exists now already. So this is the kind of architecture we are looking at. There's a machine that is to be monitored, which has vibration sensors. We're going to be looking at vibration signals, as I'll explain later. Then there's some wireless communication network sitting in between that and the decision maker algorithm, which is probably sitting in a central controller on a cloud or in house or something. So we concentrate on fault detection in machines, and we then formulate this fault detection a quickest change point detection algorithm. So this is essentially trying to find the fault in a machine looking at the health parameters as quickly as possible. We're going to formally look at what this quickest change point detection means later. So a brief on what is condition monitoring. So condition monitoring involves sensors monitoring some health parameters. For example, they could be monitoring temperature, vibration, current, wear, debris in lubrication. So for example, if something in a machine has gone wrong, then the lubrication will actually start. Let's say there's something broken, the lubrication will have those pieces. So even that can be looked at. Acoustics is some kind of sound. For example, if the fan has gone wrong, you'll know it's going to make a karkar sound, right? So that, I mean, extend that to machines, that is acoustics. So now our focus is specifically on online condition monitoring of bearing failures. So this is the reason for choosing bearings, is that bearings failures nearly make up 50% of all machine failures. So if we are able to actually help in solving this problem, then we've helped in solving a large proportion of problems. Further, we look at vibration signals from bearings. Why do we look at vibration signals? Because vibration signals are very sensitive to incipient faults. Incipient faults meaning faults which are just forming, right, at a very early stage. Not only that, measurements of vibrations can be made in a non-invasive manner. So a vibrometer or an accelerometer, which is typically used to measure vibrations, can be placed on top of a machine. You don't have to install it somewhere deep inside. So measurement can be done in a non-invasive manner. These are some motivations for picking vibration signals. Now, what is the state of literature here? So vibration, fault detection in bearings is a very well studied subject. We have literature right from 1960s onwards. In the past 15 years, there's been a lot of progress. The literature broadly focuses here though on increasing the detection power. So very sensitive algorithms exist in literature, but then these algorithms are typically offline algorithms, in the sense that they have fixed batch size processing. So they'll take n number of samples at every point of time and they process. Now in an online condition monitoring, where you continuously keep getting data, having a fixed number of samples to take a decision at every point is rather inefficient, because you're throwing away all the past information that you had. Perhaps we can improve the detection scheme. So that's what we are trying to do here. So like I said, for continuous online monitoring, our sequential approach is better, where you look at every single sample that has ever got and you take all these samples and then take a decision. We formulate this machine fault detection problem as a quickest change point detection problem, and we solve this problem. So another point is that the existing literature does not focus on the network effects in quickest change point detection itself. So this quickest change point detection itself is a very old field. Again, this has been there from 1940s. But then they never focus on what happens when a network actually comes in between the point of measurement and the point of making a decision. Typically, when a network comes in between, what happens is the samples are delayed, they can be lost, out of order samples may arrive. So these kind of these are not taken into account typically. So what we do in our algorithms is actually take these into account. So this talk will consist of 3 parts. So in the first part, I'm going to talk about a quickest change point algorithm that has been inspired by a generalized likelihood ratio procedure. So this is joint work with my advisors, Professor Andhra Kumar and Professor Rajesh Sundaresan. Then we will apply this algorithm for the specific bearing fault detection problem. And finally, we will also discuss another problem in which we bring in the network effects into play. Okay, so let's first look at what is the QCD problem. What does quickest change point detection mean? So the standard QCD problem is the following. So we are getting some. So there's a process, and from that process we keep getting measurements at a regular interval of time. Let's say those measurements are x1, x2, x3, and so on. At some point in time, let's say at time nu, something happens to the process. Maybe if you're looking at the machine itself, the machine goes into fault, or if you're looking at a fire alarm, there's a fire. Something like this happens, and thereafter, after this point time nu, we start getting observations x nu, x and so on. The distribution of these samples change because of change point. So the whole point of quickest change point detection is to find this change as quickly as possible. in the most standard formulation, it is so typically we assume that these samples are IID, and they are distributed under a distribution F naught before the change, and again they are IID after the change, and now they are distributed under a distribution F1. Okay. Again, under the standard QCD problem, it is assumed that F naught and F1 are known. Okay. So then what is a QCD policy? What is a quick exchange detection policy? It is a stopping time with respect to the observations, such that we stop when as soon as we say we have detected a change to have occurred. If we stop at a time nu t, and if the change is occurred at time nu, then the detection delay is defined to be t minus nu plus 1. This plus 1 is because even if we detect right after nu, we will just define it to be the delay to be 1. So that's how we define detection delay to be. Further, the another point of interest is the run length to false alarm. So when we are looking at a detection algorithm, we should look at what is the false alarm. So in sequential detection algorithms, the false alarm is measured using a quantity called run length to false alarm. This is defined as the following. Let's say there was no defect, okay, and then the algorithm started running at time 1, and at some time t, even though no changes occurred, we declared that a change has actually occurred. So this is called a false alarm. So I mean, this is a false alarm, right? So how long did we run to actually say that there is a detection has occurred? So this is called the run length to false alarm. A point of interest is to increase the average run length to false alarm as much as possible. This in effect results in a low false alarm rate. Okay. The conditional mean of t under the null hypothesis of no change. That is called the average run length to false alarm. That is a point. That is a okay. So then the quickest change point detection is the following. Problem is the following. We want to minimize the average detection delay. So remember, the detection delay is this. We want to minimize the average of it. Again, average defined in a careful manner, such that the false alarm is constrained. That is, the average run length to false alarm is made as large as possible. So we will use the following notation under the hypothesis that a change is occurred at time nu. The expectation and the probability the probability law are defined using E nu and P nu. Similarly, under the hypothesis that no changes occurred at all, the expected value and the probability law are defined as E nu and P nu. Okay. So what are the performance measures for QCD formally? The QCD problem in the non-Bayesian framework, when I say non-Bayesian framework, it means that there is no prior probability on when a change can occur, right? So the change point is a non-probabilistic quantity. It is a fixed number. It happened at some time. We just don't know it. Okay. So this is called non-Bayesian framework. Under this non-Bayesian framework, so Lorden proposed a certain framework for assessing the performance of the detection delay. So it is called the essential supremum average delay to detection. It is defined as following. You take this delay to detection, as I said earlier, and then you condition on the samples that were received before the change occurred, and then you look at what is the maximum, the worst possible detection delay under any set of samples. That is the essential supremum one is taking here, and then you take the supremum over all possible change points. So this is really an extremely pessimistic and a worst case detection delay. So what we are trying to do is we are trying to minimize the worst case detection delay in our work. So we are going to use this particular detection delay framework. The other performance measure is the average run length to false alarm. The average run length to false alarm is defined as the expected value of the stopping time under the hypothesis that a change never occurred. Right. So we want to maximize this. So because we want the false alarms to be as rare as possible. So therefore we want the algorithm to run as long as possible before an alarm is raised when no changes occurred. Okay. So then the minimax problem, like I said, is to find a stopping time t such that the average run length to false alarm is at least greater than some large quantity gamma that we fix. Okay. So this is basically the problem that we are trying to solve in QCD. So to solve the QCD yeah. So So you take all the stopping times such that their average run length to false alarm is at least greater than gamma, okay, and then you take the infimum of all of them. That is the this is the lowest possible. This is the best optimal stop. Right. Okay. Mhm. Okay. So n is any stopping time such that its average run length to false alarm is greater than or equal to gamma. Correct. Yes. So among all such stopping times, find that stopping time which has the least amount of, yeah, that's all. So this is the problem that we are trying to solve. So we are trying to find that particular t. Okay. So yeah. So the standard solution to the QCD problem was proposed long ago by Page in 1954. Of course, it was initially proposed as a heuristic, but later Lorden in 1971 proved that it is in fact the optimal algorithm in the sense of that minimizing that ESADD, the essential supremum average delay to detection. So at every time n, we calculate the log likelihood ratio of the measurement, and then we add to the previous CUSUM statistic Cn minus 1, and then if it is greater than 0, then we keep Cn to be that. If it is less than 0, we cut it off at 0. So this is essentially what CUSUM algorithm is. So and the Cn will keep growing and diminishing as the new samples keep arriving. At some point, the Cn is going to cross threshold h, and when it crosses a detection threshold h, we declare that a change is occurred. So this is the QCD, the CUSUM algorithm. So Lorden in 1971 proved that under the situation when the observations are IID before or after the change point, and when the pre-change and post-change distributions F1 and F0 are known, then this CUSUM algorithm is asymptotically optimal. Asymptotically optimal meaning as the average run length to false alarm is pushed off to infinity, then the ESADD is the optimal. And then Mustaqides in around 1990 proved that in fact this algorithm is optimal for every possible average run length to false alarm. So this is really optimal, okay? Yeah, for every gamma. Further, we also, and then for this CUSUM algorithm, what is the best possible detection delay? It is the following. So you choose some detection threshold h. Then the best possible detection average detection delay is of the order h by df1 f0. So this is the the Kullback-Leibler divergence between the post-change distribution and the pre-change distribution. What is this essentially saying? From each sample, we are getting on an average information equal to the divergence between the Kullback-Leibler divergence between these two distributions. So it will take so many number of samples for it to cross a threshold. That's what it is saying. Okay. So this is the average detection delay. So they showed that the Lorden showed that this is in fact true when the average run length and that the average run length to false alarm for a threshold h is greater than or equal to e power h. So these are quantities we must remember as the talk goes along. Okay. So of course this is with very yeah. So increasing h is going to increase ARL to false alarm. That is something that we desire, but it is also going to increase the detection delay. Right. Correct. Okay. So of course this is with the with F0 and F1 the pre-change and post-change distributions known. But in real world though, the pre-change and post-change hypothesis may not be known. Therefore, we consider so therefore we are going to look at composite hypothesis problems. So here we are going to look at parametric distributions. So parametric distributions are those distributions which can be completely characterized by some parameters. So take for example the Gaussian distribution can be characterized by its mean and variance alone, right? Or the exponential using its rate alone. So we look at those kind of distributions. So this is the world. So for this problem, the generalized likelihood ratio based CUSUM, GLR CUSUM is known solution to this problem. Again, this is known to be the optimal solution. The generalized likelihood, the GLR CUSUM basically does the following. At each time, if you remember, at each time what it does is it calculates what is the log likelihood ratio of the observations, and then it maximizes over the unknown quantity. Let's say the post change distribution was not known, right? That is the unknown quantity. Then it maximizes over all possible values of the unknown quantity in a set, and then this is used to calculate the CUSUM statistic at each time. So this is basically what GLR CUSUM is. So what in essence what it does is it calculates the maximum likelihood estimate of the parameter, unknown parameter, and uses this parameter to update the CUSUM statistic. This is GLR CUSUM. So now let's say this theta 1 were known, then what would happen? Then we would have this statistic Cn, right? Now this Cn and this Cn is essentially the CUSUM statistic. Earlier we showed that it can be written in this nice recursive manner. Okay. The problem with GLR CUSUM is that it cannot be written in this recursive manner, as we will see when we go along. Okay. So then why is that a problem? It cannot be written in a recursive manner, and therefore let's say we are doing machine fault detection and we've been looking at the machine for 10,000 samples arrived. Then because we cannot write it in a recursive manner, for taking a decision we should actually store all the 10,000 samples and make this decision over all the 10,000 samples. There's a huge processing problem, and so therefore we want to look at something simpler than that. Okay. So okay. So this is the GLR CUSUM. Okay. So GLR CUSUM is defined like this. You take the maximum likelihood estimate of the unknown parameter theta 1, okay, over some known set in which we think the parameter lies. Oh, okay, yeah, this should, this should be I. Yeah, sorry about that, that's a typo. Yeah. Yeah, so if yeah, let's say if theta 1 were to be known, then the supremum is going to be dropped, right? And so then this will become the CUSUM. Okay, and the CUSUM, if you can write a summation in this manner, then it can be written in this recursive manner. That is what I am showing right here. Okay, whereas this particular one cannot be written because of this, because the supremum sitting here. That's the problem with GLR CUSUM. So how do we simplify this? Well, the GLR CUSUM can be written in this manner. So then the idea is we can interchange the maximum and supremum. This is always possible, right? So let's do that. Once we do that, look at what this part of the sum is. This is essentially the CUSUM itself for a given parameter theta 1, right? So then basically what is this GLR CUSUM doing? It is taking a supremum over CUSUMs for each parameter theta 1, right? So of course when theta 1 is in a the capital theta 1 here is a continuous set, then it doesn't really simplify a problem in any manner. Now, but let's say this capital theta 1 were to be a finite set, then essentially what we have is a set of parallel CUSUMs running, and whenever any of these parallel CUSUMs cross the threshold, we declare that a change has occurred, right? So this is how we can simplify this problem. So this comes to so now what happens, but then what do we do when the post change parameter set is not finite? Can we do something then? So let's say we have the situation here. There's our pre-change parameter, let's say, is called theta naught, okay, and the post change parameter is lying in some known set capital theta 1. It's somewhere, some point in this set. Then what we can do is that we can select a finite subset of this capital theta 1. Okay, let's say we call that subset theta 1 hat. Okay, so then so I mean, of course, for that this capital set theta 1 must be a compact set and so on and so forth. Only then we can discretize the set. But let's say those conditions are met and we are able to do this. So then of course, what we propose to do is that instead of searching over all of this set, we search over only of this smaller subset theta 1 hat. That is essentially what our GQSUM algorithm is going to be. So then the question arises, how do we choose this subset? One way to sample the subset is to have the elements in the subset that to be separated by a constant information distance. What is information distance? It is Kullback-Leibler distance, right, between the distributions. So we choose these points in the theta 1 hat to be using this. This is basically again this basically ensures the following, that any point here is in such a way that it's at least delta away from one of these other points. That's how we are choosing this set. So delta is going to be a design parameter in our algorithm, as we'll see going further. Okay, so then our algorithm is the following. So this is the formal setting of our algorithm. So we are given observations xk, k1, 2, and so on. Nu is known, is a change point which is not known. We have the pre-change distribution parameter theta naught to be known, and post-change distribution parameter theta 1 is going to be unknown, but we know that it belongs to some known set theta 1. This again we say that this we assume that this theta 1 is a compact set and so on. So then our CUSUM algorithm is the following. You say, given a user parameter delta, the user will set this parameter delta, and this delta is going to influence the performance of this algorithm, as we will see further. We will choose a grid set theta 1 according to this discretization procedure that I described earlier, and at each time n, we compute the CUSUM statistic for each of those each of these quantities inside the set theta 1 hat, and then the stop whenever any of the when the first CUSUM here stops. Okay, that's our GCUSUM algorithm. Yeah, it's basically this. So this is saying that any point here is at least delta away from one of the points in the grid set. Yes. Right. That's all. Okay. Okay. So so then what do we have? We have asymptotic analysis of the performance of this GCUSUM algorithms. So our performance analysis is valid for a general class of distributions under the following assumptions. These are technical assumptions. Basically, most of the common distributions all have these assumptions. So there's no issue there. So having made these assumptions, we provide upper bounds on the average run length to the detection delay, and upper and lower bounds on the average run length to false alarm, as we further. So we show that there's an upper bound on the average delay to detection. So remember that we had this parameter delta. If you remember, CUSUM had this much delay, right? H by the Kullback-Leibler distance between theta 1 and theta 0. Now, because we have introduced that discretization, a penalty of delta is imposed. So this is how the SIDD changes. So as you make delta coarser, the number of points in our set is going to decrease, so number of CUSUMs will decrease, but then we'll have a larger delay, right? So basically then the upper bound is a function of the user parameter delta. The GLR CUSUM, which I had shown earlier as the optimal algorithm, had an ESIDD of this much. So what is the penalty that we are suffering? We are suffering a penalty of delta. But then what is the gain that we are going to get? So yeah, this is what we say. The gain that we're going to get is in the average run length to false alarm. Remember that so the average run length to false alarm was defined as the expected value of the stopping time t under the null hypothesis, right? So this is the asymptotic amount of value of this, and what we are saying is that it is of the order e power h here. If you look at it, basically it is saying this is of the order e power h, and that's what it's saying. Whereas for the GLR CUSUM, which we said as the which was the optimal algorithm, the average run length to false alarm is of the order e power h by root h, that it is less than this. Why do we get this performance gain, so called? This is because these are really a set of finite number of parallel CUSUM. So therefore, for CUSUM we saw that the average run length to false alarm is of the order e power h. So therefore, we'll expect that even our GCUSUM is going to have this. So why are these bounds actually useful? Why did we do all of this? Because remember that we had to choose a threshold h for the optimal detection, right? Now the difficult part in all of this sequential detection algorithm is choosing that h, because running a simulation to find what is the h is really hard, because very long simulations. So therefore, by providing these bounds, we are actually decreasing the search space over which you have to find that right h. Getting an optimal h through theory is actually very hard. So these bounds are going to help in that manner. Okay. So these quantities beta have closed form expressions only for certain distributions. Otherwise, they have to be computed numerically. Now having done this, shown this algorithm, we are going to apply this for bearing fault detection. So let's look at what bearings are to start with. So a bearing has the following structure. So basically it has four components essentially. There's first an outer race, okay, this is a ring, and inside that there's an inner race, there's an inner ring, and inside between these two rings there are some rolling elements. Here we have a ball, it could also be a small cylinder which are rolling, and to keep these rolling elements from hitting each other, there's a cage that holds them away from each other. Okay, so these are the four elements. A defect can occur in any one of the four elements. So whenever a defect occurs, what happens? So let's say a defect has occurred on the outer race. Okay, the defect could have occurred anywhere else, but let's consider that. When it occurs, the rolling elements are running. Remember, in this bearing which is working in a machine, and when they're running, these rolling elements are going to hit one of the point at which a defect has occurred, and every time a hit is occurring, there's a impulsive force that is happening. So and because the bearing is running at a constant frequency, these impulsive hits are coming at a constant frequency. The frequency between these hits can be found out, as I'll show you next, as the fault frequency. So depending on where this particular hit has occurred in this bearing, and depending on what is the frequency, I mean the speed at which this bearing is run, this fault frequency can be found out. This is there in any textbook. Okay, so the way this why does this result in vibration? Let's see this. So this, remember that these hits are occurring and are generating these impulsive forces. This is finally detected by a vibration meter sitting somewhere, right? So there's this distance in the machine. There's a distance from the point at which this hit is occurring to the vibration machine, vibrometer. So that whole part is actually some object which has it has some characteristic frequency, right? So it has a characteristic for vibration. So so what happens is, every time an impulsive hit occurs, it is then modulated by how much load is there on the bearing at that particular point, and then it is and then there's this like I said, the particular machine has a vibration response that is called h of t, and this results in a vibration signal v of t. This is what we are seeing every time when a bearing goes into defect. Okay, so the vibration signal can be modeled like this. As you can see, this is actually a periodic signal. There is no randomness here. Okay, so for all of this is available in standard textbooks. Now, how does actually vibration signal look like in real? So look at so here we plot the RMS value of a vibration signal when a bearing has entered a defect. So in the beginning of this plot, we show when the bearing was working fine. At this point, the bearing is actually gone faulty. So the vibration signal's RMS value keeps increasing. So we can just look at the RMS value and detect. Or here we show the excess kurtosis of the signal, even that keeps increasing. Maybe we can just look at this. But in real, when the machine is running in a factory and there are a lot of noises, these particular signals are buried under noise, and therefore we'll have to look at it more carefully. Now let's look at what happens to the frequency spectrum of the vibration signal. During normal operation, the frequency spectrum of vibration signal looks like this, right? When the bearing has actually gone completely faulty, it looks like this. We can clearly see that there are these particular frequencies which are sounded, right? Just when it has started to go into error, this is how it looks like, and this is the particular point at which we want to detect that a fault has occurred. Okay, so basically these frequencies at which they are sounded are all harmonics of the fault frequency that I mentioned earlier. Okay, so and where is the maximum of, so one thing to do is to just check if these frequencies are being sounded or not. Again, there's a lot of noise under which this is buried, so a simple strategy like this is not going to be very effective. Okay, so then we look at more sophisticated signal processing for analyzing these bearings. So earlier I showed you that the impulsive hits are all perfectly periodic, but in real, what happens is that when the bearing has load on it, the rolling elements actually slip while they are running through that between the rings, and this slip causes a slight change in the impulsive hits. There's a slight bit of randomization that is generated, and this jitter results in the bearing vibration signal actually becoming cyclostationary. What is cyclostationary? What is a cyclostationary signal? A cyclostationary signal is any signal whose statistical properties are periodic. So for example, the variance could be periodic. Okay, So the cyclostationary signals can be characterized by the spectral correlation density. Remember, for stationary signals we have the power spectral density, right? This is the counterpart for a cyclostationary signal. This is called spectral correlation density or cyclic spectrum in short. So for a cyclostationary signal, this is how this cyclic spectrum looks like. If you just look at the first part of this is the PSD, okay, and these are higher orders parts of it. So this is the cyclic spectrum is a two-dimensional function. Okay, so like I said, the bearing vibration signal is a cyclostationary signal. So cyclic spectrum measures what actually is a cyclic spectrum. It is the correlation between frequency components at f plus or minus alpha by 2. Okay, that is what cyclic spectrum actually is. So where alpha is called the cyclic frequency and f is called okay, so alpha is called the cyclic frequency and f is called the harmonic frequency. Okay, so detection strategy is to check for correlation at frequency components f plus or minus alpha by 2. Okay, assuming so what we know is that for bearing faulty bearings, alpha is known to be equal to fd. Again, fd, like I said, can be found in any textbook, so alpha is known, but we don't know what f is, which f to look for, right? So that is going to be a further challenge. So vibration signals from faulty bearings are cyclostationary at frequencies equal to this faulty frequency, that is alpha equal to fd. So what we're going to do is through cyclostationary processing is that we are also going to filter out stationary noise. Remember that when stationary noise is looked at, it is perfectly stationary signal. So therefore, at the cyclic frequency alpha, the stationary noise basically adds 0 component to it. So this is very good signal processing, and therefore it helps in bettering the performance also. So then what is our algorithm? Let's say we have a L batch of samples of vibration signals, then we select a DFT size n, and then we find the short term Fourier transform of signals, and then we take the correlation between frequencies which are FD apart. Okay, so our analysis of this algorithm assumes the following. We assume that, let's say first I told you that spectral frequency f is not known, right? So let's to start with assume that f is known. It is given given that there is a particular frequency at which if we check, we'll get good detection. Okay, so let's say that f is known. Then we also assume that the Fourier transform at each frequency R0 means circularly symmetric Gaussian random variables. This can be motivated from Fourier theory, asymptotic Fourier theory. Okay, we'll also assume that DFT coefficients across several windows that we're going to take are all uncorrelated. So then the problem basically boils down to the following. So the statistic that I showed earlier, pre-change has a covariance matrix which is diagonal, and the statistic under the post-change has a covariance matrix which is not diagonal. So we have to just check this particular hypothesis. Okay, so further it is also known, the structure of this particular matrix is also known, because after the fault has occurred, the RMS value of the vibration signal increases. So therefore, from D this R11 is going to be higher, and from D this R22 is going to be higher. So this is already known. Okay, so then basically we use that particular statistic that I showed you earlier in the page along with GQSUM to detect in the change in the covariance. Remember, the GQSUM was that CUSUM algorithm that we had designed. Okay, so with this is the kind of performance we get. So this is a this is the Neyman-Pearson test with the statistic that we had proposed. Okay, so these are some other competing algorithm in literature. So the just Neyman-Pearson test with this particular statistic itself gives a huge benefit. Now if you add on top of it sequential detection, that gives even further benefit. So this is the kind of detection improvement we see. And here we've plotted what happens when, let's say, remember this is the point. What we are assuming is the post-change parameter is not known, right, for the statistic. But let's say it was known, then we get a detection performance in this manner, where but we suffer a loss in performance due to that detection parameter not being known. And see, as the SNR gets better and better, the performance gap between these two algorithms reduces. This is because we are able to estimate the parameter better and better. Remember, we did an ML estimate of the parameter for GQSUM. Okay, so now here we have assumed that the best frequency were known, but let's say the best frequency is unknown, right? Because in practice it will not be known at what frequency we have to look at. Then what do? Then we look at multiple frequency. Let's look at all the frequencies and then choose from it. So this, of course, for this to work, we'll have to assume that the Fourier transforms are independent across frequencies. Again, this is a valid assumption based on asymptotic Fourier theory. With that, we formulate another statistic called S multi-frequency using cyclostationarity, and then we use CUSUM algorithm along with it. So basically this boils down to running a QCD algorithm on several frequencies. That is, there are multiple QCD algorithms running at each frequency. The change could have occurred only in some of the subset of the frequencies. For this, there are existing algorithms in literature. We use something called the sum QSUM. With that, we see a huge increase in performance. Remember that this blue, so this yellow curve is what we got with a single frequency. This red curve is what we get with when we use multiple frequencies. We are not plotting any of the competing algorithms here because this curve, they are very bad. So as we'll see in the real vibration data sets that I'll show later on. So here we show the performance of our algorithms on real vibration data sets. So we have existing vibration data which is available in the form of data sets available for download. So there's a Case Western Reserve University vibration data set. This is considered the standard data set in literature for checking vibration algorithms. On this, EES is one of the best competing algorithms in literature. The EES is, so this data set consists of 52 different signals. We are able to detect a defect in all the signals, whereas EES only detects a defect in 46 of them. And similarly, there's a certain FE data part of this data set. Again, EES is able to detect only in 47 of it, whereas we are able to detect in 52 out of 52. Okay, then there's another vibration data set called the IMS data set. This is from the University of Cincinnati. Here again, what we are tabulating is how quickly our algorithms are able to detect a defect. So the competing algorithm EES detects a defect at a 704th index, whereas we are able to detect it much earlier. So in essence, what we are saying is our algorithm actually shows substantial improvement in performance. Okay, now we quickly move on to the next part of the work. I remember I had promised that we are going to look at QCD over lossy networks as well. So this is joint work with my advisors, Professor Anurag Kumar and Professor Rajesh Sundaresan, and Professor Arpan Chattopadhyay from IIT Delhi. So this is the problem that we look at here is the following. So we have a sensor which is monitoring machine health, and there's a decision maker which is away from the sensor on a wireless link. This wireless link is assumed to be a lossy wireless link. Okay, we will assume a slotted channel here. The wireless link is going to be we are going to impose a slotted channel. So an example of such a model is the 6-dish itself. So we will assume that the sensor monitoring this machine health transmits the measurements on packets. And in the slots, this is how it's going to happen. So at the beginning of each slot, if there's a measurement to be transmitted, it is transmitted, and within that within the end of that time slot, an acknowledgement is received if the packet was successfully received at the receiver. Okay. Then we will also assume that the packets are retransmitted until success. So this essentially means that there is no loss of measurements itself, but the measurements can be substantially delayed. So we will also assume that the link quality, that is the wireless link between the sensor and the decision maker, is going to change with a change point. Why is this possible? Let's say after the machine is actually degraded, typically what happens is because of the increased vibration, the temperature of the machine will change, and this can result in the change of the channel itself. So that's why we will assume that the link quality changes with a change point. Again, we are going to use the non-Bayesian QCD framework. We are going to use Lordan's minimax framework that I showed earlier. And we will look at the detection delay analysis in the asymptotic regime. So the summary of our contributions here is the following. So this particular problem of QCD over wireless networks has not been very well studied. The only paper that we saw in literature is Prem Kumar's, who is an alumni of our department. He studied this problem in a Bayesian setting. We are going to study it in a non-Bayesian setting. our contribution is the following. So we look at the problem of QCD with losses and delays due to channel, under the assumption that the channel loss probability also changes after the change has occurred. We show that this problem reduces the quickest change detection of a Markov process, and that our proposed CUSUM based algorithm is asymptotically optimum as the average running to false alarm goes off to infinity. Okay, then we also do some non-asymptotic average study, and then we show what is the effect of sampling and queuing on the detection performance. Okay, so here is a system model that we are considering. There is a sensor that is monitoring machine health. Maybe there is a vibration signal which is being monitored, and it is being transmitted over a lossy channel which is slotted, as I said earlier, to the decision maker. At each time, a sensor is going to produce a measurement, and the measurements are packetized, and in each slot one packet is going to be transmitted. If a packet is successfully received at the receiver, an acknowledgement is received in the same time slot. If it is not successfully transmitted, then it is queued in a transmit queue for retransmission. The sensor is assumed to generate samples at a rate r, which is less than 1. These measurements are going to be labeled as x1 to x2 and so on. We will assume that a change occurs at a time nu. This corresponds to, let us say, the bearing going faulty. We will assume that the samples xk are distributed by a distribution f0 before the change and f1 after the change. Again, in this piece of work, we will assume that the pre-change and post-change distributions are known. We will also assume that the channel loss changes from P0 to P1 after the changes occurred. We will assume that the sampling rate is less than the minimum of P0 and P1. This is to ensure that the transmit queue is stable. Slot k of this slotted channel refers to the time from k minus 1 instant to k plus k. This is just after the kth instant. So any sample that has been generated in this time is counted into the queue at this point. The queue length at the beginning of the time slot k is called qk. If the queue is non-empty, then a transmission is attempted. This particular so that's for so whenever the queue is non-empty, a transmission is attempted. So basically, any sample that has been generated in this time is then transmitted here if the queue was empty to begin with. Right, the decision maker then observes these quantities yk and zk after a transmission occurred. What does yk encode? Yk encodes whether a transmission has occurred or not, and if a transmission occurred, is it successful or not. So basically, whenever a successful transmission occurred, yk is 1. On unsuccessful transmission, yk is 0. If the queue were empty, no transmission occurred, then yk is equal to this null. And then if a successful transmission occurred, then zk encodes the received measurement at the decision maker. Okay, so this is our notation. So then the formal problem statement is the following. The QCD problem then is this. Okay, so if you remember earlier for the QCD problem, we had x1 through x nu minus 1, right? Now we have z1 through z nu minus 1 and y1 through y nu minus 1, because these are the observations at the receiver. Okay, why is this problem complicated from earlier? The principal challenges are, earlier we had assumed IID. Okay, now this y1 through y nu minus 1 is not IID. Okay, so y encodes whenever the queue at the beginning of the time slot k qk is non-empty, a transmission is attempted. Okay, so yk, yeah, it could have. No, we discussed that which packet to send is discussed later. Now we are saying one packet. No, we are sending what is the head of the queue packet. That is the oldest packet. For this particular analysis, we are sending the oldest packet. Yeah, yk encodes whether if a transmission occurred, and if a transmission occurred, is it successful or not. So if a successful transmission occurred, yk is 1. And it also encodes whether a transmission occurred. Let's say the queue was empty, then yk is null. Okay, and zk is the actual received value. Yeah, and when no unsuccessful transmission, it is variation. Yeah, yeah. So so then, okay, so now the principal challenge here is that these are not actually IID. Why is not IID? Now remember, note if yk is phi, that is if at a time k no transmission occurred, it means that the previous transmission in the previous slot either a successful transmission occurred or there was no transmission at all. It is not possible that yk is phi and whenever yk minus 1 is 0, right. So this means that they are actually correlated. So this is no longer IID. Okay. Also remember that there is a essential supremum and a supremum sitting here. Whenever nu goes off to when as nu keeps increasing, what is the worst? I remember I told you that this essential supremum is what is the worst possible combination of this of these quantities that can result in a delay. What is the worst possible combination of these quantities? That every single time an unsuccessful transmission occurred, right? So up until nu, y could completely be just unsuccessful zeros, right? So that is the worst case. So as nu goes off to infinity, this actually I mean, at the first look, this problem is cannot be solved at all because this always goes to infinity. But then we show that it can be solved. So then, what is our QCD algorithm? We will assume the following. We will assume that at the beginning of the QCD, the Q length is known at the decision maker. We will assume this much. Okay. QCD will start at k equal to 1. Then we will nu is the change point. Okay, so this is unknown to the decision maker, but the analyst knows it, of course. They are Bernoulli. They are with a Bernoulli with rate R. Yes, there is some stochastic. That is the channel model, right? So yeah, the channels also. It is IID, yes, yeah. Correct, yes. That's what saves us. So we'll define the log likelihood, we'll define Li like this. So Li is basically this, okay. Whenever a successful transmission occurred, how much information is received is exactly this. This is the information from the received data. Whenever any transmission occurred, then the indicator of whether the reception is successful or not is going to give us some information on how good the channel is, whether it is a pre-change channel or post-change channel. So this is, we'll define this quantity Li to be equal to this. Okay. Then our QCD rule is a CUSUM algorithm that uses this Li as the updates. So that is our QCD algorithm. H again is the decision threshold, which is based on the ARL to Fa constraint gamma. So for this algorithm, we will show what is the asymptotic analysis. Okay, it is so for the asymptotic analysis, what we'll do is we'll define an augmented observation space. Remember that the decision maker only looks at yk and zk, but the analyst knows zqk. So we'll define a new observation space called zeta k, which includes qk also. And then if we look closely, it turns out that zeta k is actually a Markov process. Okay. Then through some algebra, we can show that the log likelihood ratio of this Markov process can be written down nicely in this manner. Again, remember there is Li dependent only on that particular the observations at time I, right? So it can be nicely written down in this manner. So then what happens is this problem actually reduces to the QCD of a Markov process zeta k. Now what is the state of art for the QCD of Markov process? QCD of Markov process has been studied by Akir and Mustakides, and it is right now, at this time, it is not known whether CUSUM is the optimal algorithm for QCD for Markov process at all. But it just turns out that for our Markov process zeta k, this particular QCD algorithm actually turns out to be optimal. So for that, to prove that, we use the framework of Lai in 1998. This is an asymptotic analysis framework for non-IID processes. How do we do it? So we take the log likelihood ratio and then we take its average as n becomes very large. And so for this Lai's analysis framework to work, we need to show that this particular quantity, the average value of this, concentrate towards some quantity I. Okay, and let's call that quantity let's call that quantity I. Okay, for IID processes, if you look at this, what is this? This is the log likelihood ratio as n grows larger and larger, and we take the average value of that. That is exactly equal to Kullback-Leibler distance. But for non-IID processes, I could be some other number, right? So for our Markov processes, the way we do this is let pi p1 be the post-change stationary distribution of our Markov process. Then the I is defined in this manner. It is the expected value of the log likelihood ratio, the L, the quantity that I showed earlier, under the stationary distribution, post-change stationary distribution. Okay, so by ergodic theorem, we can show this is actually true, and then we can also show that I can actually has a closed form expression in this manner. What does this mean? So this means the following, right? So that information is being generated at a rate r, right? So that is the amount of information, and it is, and this p1, whenever a successful transmission occurs, this much information is coming up. So we can actually show this. We'll see this later. So so then what do we have? We have that the we have a lower bound on the ESADD, and we show that lower bound on the ESADD is exactly equal to this. That is log gamma, where gamma is the ARL to FA threshold that we have, divided by I, as gamma tends off to infinity. Then we also show that there is an upper bound on the ESADD for our CUSUM algorithm. For a given threshold h, it turns out the upper bound is of this manner. So basically what we are saying is, if we use a threshold equal to log gamma, h equal to log gamma, then the average relative reduction is of the order h by I. So this is what we've shown, and we know from Laurent theory that this is in fact the asymptotic. So this is in fact the optimal detection delay. So what this shows is that our detection procedure is actually the optimal detection procedure. Okay. So to show that our asymptotic analysis actually works in practice, here we've shown what is the delay to detection as h tends off to as h becomes larger and larger. As you can see that this approaches 1 by I. When we plot ADD by h, it approaches 1 by I as h becomes larger and larger. Okay, so why is it so far away from 1 by I when h is smaller? It is because there's a lot of non-asymptotic artifacts, as we'll see, whatever they are. Remember that there is a queuing delay component, and then there's sampling delay component. All of this is not accounted for in the asymptotic analysis. But when you look at smaller h's, right, those become very significant, and that is the difference that you see between these two curves. Okay, so the average delay to detection actually in this case consists of three terms. That is the decision delay. Decision delay is if there is no network sitting in between the measurement samples and the decision maker. That is just the decision delay. Queuing delay is because of the transmit queue, and sampling delay because of the irregular sampling that is happening. Now for large values of h, the decision delay is of the order h by I. But when sampling rate is chosen to be very close to the channel success probability, then what happens is the queuing delay will shoot up, right? Similarly, when the sampling rate is assumed to be very small, the sampling delay will shoot up. So this again we show, we'll see what are the effects here. So here we are plotting ADD minus h by I. So we are only plotting the non-asymptotic part of the detection delay here. So we can see that when the sampling rate becomes closer and closer to the channel success probability, the delay shoots up. This part corresponds to the queuing delay. Okay, as the sampling rate becomes very small, this again the detection delay shoots up. The total delay shoots up because this is really the sampling delay. Okay, so in practice one has to choose the sampling rate carefully so that it doesn't shoot up like this. Okay, so then we also show that this can be extended when packets are lost. I'll just skip through that, but now this pertains to the question that Professor asked on should we always choose the head of line packet first. Okay, so again this is our model. So this is the packet, HOQ packet is head of the queue packet is the oldest one. So the most recently sampled measurement typically contains the latest information. So that corresponds to the last come first serve queuing discipline. The first come first serve queuing discipline is the head of the queue packet, which is the oldest packet. So which what do we choose? Do we choose LCFS or do we choose FCFS, or we choose some other queuing discipline? So so when packets are delivered at the DM out of, so then depending on which queuing discipline we choose, the packets delivered the decision maker will now be out of order. So then how do we change the QCD algorithm to account for this? This again, this also we investigate. So we will consider non-idling queue disciplines. What this means is that there is, the queue is never idle. Okay, the packets will keep coming. At the end of each busy period, what happens is the queue is completely emptied out. Right, at the end of busy period, whatever transmit queue discipline you use, the detection delay is the same. So what we are looking at is only within a busy period. So within one busy period, what is the best strategy to use? So remember that the DM observes Yk, Zk. Now in addition, we have another quantity Jk. So Jk is the sampling time of the measurement that has arrived at time k. We need this because if the measurements are now coming out of order, then they'll have to be rearranged in a proper manner. So to perform CUSUM, what we do is at the DM, having received all these samples, we rearrange them based on the sampling time to this. Okay. Once they have rearranged, we just do the usual CUSUM, and then we show that this is actually the right thing, and in fact, this is the optimal thing to do. We've shown it through analysis. The main result of our transmit queue discipline work is the following. Under the assumption that the likelihood, the post change and the pre change distributions are likelihood ratio ordered in the following manner, we show that the CUSUM statistic with the first come first served discipline and the CUSUM statistic with the LCFS discipline and the CUSUM statistic with any other non-idling discipline are ordered in this manner, and this ordering is the stochastic ordering. Okay. That is, the CUSUM statistic with the FCFS is the lowest, and the CUSUM statistic with the LCFS is the highest value. Of course, the highest CUSUM statistic is going to hit the threshold first, right? So this is going to result in lesser lesser detection delay for the LCFS discipline. So basically, our main result is following. Under this assumption, we show that the stopping time under the LCFS queuing discipline is the lowest among all non-idling disciplines, and the stopping time of the FCFS discipline is the highest among all non-idling disciplines. So we show this. This is our main result here. So again, remember that the received samples under the probability of no change have all the same distribution, and therefore regardless of what queuing discipline we use, the asymptotic performance is going to be the same. Further, the ARL to FA is also going to be the same. So there's no difference in the threshold that we choose. Okay. So to conclude, sorry, I've been over time. We've studied the QCD for composite post-change hypothesis problems. We and proposed GQSUM. We formulated the machine fault detection problem as a QCD problem, designed cyclostationary based statistic, and applied our GQSUM and showed that our algorithm has vastly superior performance compared to literature. And then we studied the QCD problem when network delay and losses are present, and we showed an optimal algorithm, and also investigated the effects of transmit queue disciplines of QCD over networks. That's all I had. Thank you.
Thanks a lot, Krishna, for the informative talk. So please feel free to ask questions if you have any. Any online questions? We will conclude this talk now. So we have arranged the refreshments at the coffee hut. Please feel free to continue discussions at the coffee hut while having refreshments if you have any. Thank you.
Thank you.
Thank you all, and have a great evening. Thank you, Krishna, once more.